So in the last video, we were talking about continuity. Now we're going to talk about differentiability. Differentiability is actually a stronger, a stronger condition than continuity. Differentiability, instead of saying, can I just put my finger on this line and trace it along without ever having to pick up my finger? Well, differentiability has to do with the question of, is it actually smooth? Okay? So, a function is differentiable at a if f prime of a exists. Okay? So, we have a couple other statements saying that if a function is differentiable, at a okay. So if a function is differentiable, then it is continuous. But so differentiability is a stronger condition than continuity. So if you have a function that's differentiable at a point, well, it has to be continuous at that point. But just because something is continuous at a point does not mean that it is differentiable. Okay? So differentiability has to do with smoothness. And so if we consider a problem, this appears in stock market analysis, fractals, a lot of actually really applicable things in mathematics. So if you had something, let's say like this. Right. And let's say this thing is so just crooked and messed up that if I zoomed in, let's say on this little space right here, okay, let's say I blew it up. And no matter how much I zoomed in, it was just still wigglier and wigglier. This concept of zooming in and the same image popping out is what's known as a fractal. It's used a lot in actually in making like Pixar cartoons and stuff like that. They use fractals to build things like a tree, and it has the concept that if you were trying to outline the coast of England or something like that, and you just kept zooming in and zooming in, you'd find smaller and smaller bays. Something like this is continuous. I can put my finger on this, and I can still wiggle around. I don't have to pick my finger up. But it's not differentiable. And so why would this thing not be differentiable? If I try to calculate the instantaneous rate of change of the slope at any point in part of this problem, I couldn't do it, okay? So if I try to calculate the slope here, well, if I go from the left, remember that the definition of the derivative is also a limit. So if I approach from the left or the right, it has to be the same thing. So if I try to calculate the slope right here, that's got a positive slope. Then all of a sudden it switches to being a negative slope. So this is something that would not be differentiable. So how am I going to put this on y'all's test? I'm going to ask you the question, find the interval of continuity, and then I'll give you a different graph and I'll say, find the interval of differentiability. So what I'm going to do at this point is look at the comparison between the two problems, okay? So, we'll call that 8. We'll call that point, symmetric, we'll call that -3. Call that -5. And we'll call that negative. And so we're going to examine the concepts of differentiability versus continuity in relationship to this problem right here. Okay. In this class, never put a bracket when we're talking about differentiability. There are concepts in math about if something is differentiable from the left to the right, but we're going to ignore that concept for calculus. It gets more into analysis. So when I was teaching my analysis students last year, we covered the topic, but for calculus, just ignore it for right now. Okay? So, first, let's say, what is the interval of continuity? Okay. So, if I'm going to start over here on my left, -8. Okay, now I can take this. Now I've got a hole. Okay, so -8 all the way up until 3. So I've got to break it 3. And then, it's going to go all the way up to 8. And we're going to put a bracket because that is an endpoint. I'm trying to fit this all where you can see it. So, okay, so we start at -8. Okay, so you have to imagine, where is this thing smooth? Okay, well, if I got up to that point right there, what's going to happen? If I try to calculate the slope in this direction, it's going to be positive. If I try to calculate the slope in that direction, it's going to be negative. I've got no way to determine the slope at that point. So that point right there is our first point of differentiability. Non-differentiability, excuse me. Okay. Hopefully, if I can see this. All right, and so for my next point, I'm starting at -5. I go all the way out to this point right here. Now, if I try to calculate the slope at this point, it's negative. Then all of a sudden it switches to being positive. Okay? So at that point, I can't calculate its slope. So that's my next point that is not differentiable. So that would be -5 to -3. And then union, okay, we go -3 all the way to 0. And then union, 0 to 3. And union, 3 way up until 8. And we're not going to put a bracket on any of that. Okay. So you can see by this, how many breaks do we have when we're talking about continuity? We only have 1. Okay? That was at 3 because we have a hold at 3. But when you talk about differentiability being so much more of a stronger condition than just continuity itself, where do we have the breaks? We have a break of differentiability right here. We have another break of differentiability right here. We have another break right there. This point ain't even continuous, so it's definitely not differentiable, because remember, one of the statements I said just a minute ago was that if a function is differentiable at a point, then it's continuous at a point. So if a function is not continuous at a point, it's definitely not differentiable. Okay? And then all the way up to this point right here, we don't talk about differentiability at endpoints in this class, so it is always going to have parentheses. So just as a rule of thumb, when it comes to y'all's test, continuity at an endpoint can get a bracket, okay? As long as the hole's filled in. But whenever you're talking about differentiability, it's parentheses everywhere. Yep. So
I have a question. I was a little confused. If it's not differentiable,